Okay. Hello, everyone. Welcome to the lecture number 13. And so previously we talked about, as you can see here, Born-Markov approximation plus secular, where we derived in a series of approximations, we showed that any generic dynamical map for some generic open system S tends to the Davis map generated by Davis generator LDAV, we denoted it, that is in the GKLS form, and that gives us the famous master equation formulation for our open system dynamics. So today I want to use this result and apply it to some also fairly generic situation, namely I want to use the methods of open system theory, master equation in particular, to analyze the dynamics of thermalization. So what is thermalization? So imagine that we have a system S, some small system S, right? And also we have a big, complicated, big in quotation marks, system E that we'll call buff. And the system is in thermal equilibrium with inverse temperature beta. So this is inverse temperature beta, standard definition, Boltzmann constant times temperature, 1 over it, right? And now we want to make the system S to be in contact with the buff, right? And the intuitive expectation, right? I mean, it's not only intuitive, this is something we will always learn in thermodynamics, statistical physics, and stuff like that. That this system S should, over time, be brought to a thermal equilibrium with the buff. That is, due to interactions with this huge reservoir of temperature, the system state should asymptotically reach also a thermal equilibrium state at the same temperature as the buff, right? So this is this standard point of view. We always thought and we believe intuitively that this is a very robust process, that it will happen almost every time for every buff, for every system, and so on and so forth, with very few exceptions. But this is also a setup that's like perfectly fitting the open systems paradigm, right? Because we have a system S, we have the environment, the buff, right? And we might try to actually witness or describe and analyze the dynamics of this process using the concepts like dynamical maps, right? And master equation and things like that. And this is what I want us to do today. And, to look if we can describe these dynamics, and if we can, to see how it works, and maybe even determine how robust it is, what are the sufficient conditions for it to happen, and in what circumstances it might break, and maybe understand the physics of the process a little bit better. So let's try to do that then. So let's put in some definitions here first. So we want system S and buff E to be interacting. So let me start with specifying what kind of Hamiltonian I have in mind. So I will have our system buff Hamiltonian will be fairly generic. So we will follow the convention we used so far. So we have a bare system only Hamiltonian as HS0. We have a Hamiltonian of the buff HE, and we have a coupling, right? This one is fairly necessary, fairly required to actually get anything. But I won't use the just to simplify our analysis. I won't be using the most general form of the coupling. Let's just focus on the simplest incarnation of the coupling that we can have. So there is just some operator S times operator E, bare operator E, right? So this is a coupling on the side of environment, and this is a coupling on the side of the system. And we will also, I will also assume the initial state, So rho SE of 0 will be some arbitrary density matrix on the side of the system times a thermal state on the side of the environment. So this would be the, sorry, wrong letter, E minus beta H E, right? And this so thermal states, I will use letter P to indicate them in index information about the temperature, about the beta here, and superscript just to indicate the which system we are talking about, or rather which energy operator we are using to define the thermal equilibrium, right? So setting this state here, this is what defines for us that the system E is a buff, actually, right? Because this is where the temperature comes in. And the other thing to note is the thermal state is not only given by the temperature, right, but also the energy levels, right? So energy operator representing the energy. So in case of the buff, we are taking here just the free Hamiltonian of the environment, HE. So if we have the initial state specified, so we will also, of course, as usual, do the standard thing. We will define here we will shift our system Hamiltonian and the coupling. Right, we learned the hard way on previous lectures that this is always a good thing to do. So we'll have SHS times 1 plus 1 times HE plus lambda S times F. Right, and I didn't plan it too well. Maybe let me change the color. So the shifted coupling, this guy here equals the bare coupling, right? Minus trace over E, the expectation value of the coupling. So we should take here I mean, typically we take here the Heisenberg picture or the interaction picture for operator E with respect to the free Hamiltonian of the environment, HE, but the thermal state, because it is basically a function of the Hamiltonian, it commutes with HE, right? So this means that the expectation value, the interaction picture is just spurious because it's everything cancels here. Now, You know what? Maybe let me show it here. So the environment is stationary. So we can, just from the very definition of the initial state of the environment, the equilibrium state commutes with the Hamiltonian, which implies immediately that you get trace, you get operator in an interaction picture. So you take something like this, right? HEP E beta. So now, because we have this commutation relation here, so I can take this guy here and just move it past the initial state. Right, so we take the evolution operator, we commute it with P, then we use the cyclic property of the trace to move it to the left side, to pop it here, and here you have E minus ETHE times EITH HE, so they cancel, right? So after we commute everything, we get I minus T HE EI THE. So because we can shift evolution operator past the initial density matrix, this what this allows us to reduce dependence on time, right? Which means we have a stationarity here, and this thing is just identity, right? Hence we are shifting by a constant here, by a constant operator. There's identity here also. And then if this is the shift of the coupling, so the Hamiltonian also gets shifted. So it's Baer Hamiltonian plus lambda trace E PE beta. Oh, not enough room, sorry. Beta S. Right, the standard stuff. The thing that simplifies things is that we have stationarity, so this correction here, the shift is time independent, so everything is constant here. So that's the standard setup, right? We typically use. What else? Right. So let's go back to the purple. So now we will be working in here. We assume weak coupling. Weak coupling regime here. So we assume that the lambda times correlation time of our buff to be small, right? So that we can justifiably use the Born approximation from the previous lecture. That is, if we consider the evolution of the reduced state of S, so we have our dynamical map, E minus IT HSE rho 0 S times thermal state. Right, and we can weak coupling regime so that we can justify the lowest order approximation to the supercumulant expansion. That you can write that we will approximate this guy here with a map of this form, IT HS, shifted Hamiltonian, times TLE minus lambda square integral 0 to TL2 U0 du acting on the initial state of the system. Right, so this is Born approximation we used previously. So Born approximation, second order. Just as a reminder. And now what we are, so the dynamics we are interested here is a long time behavior of the, so we want to show that over time, asymptotically, the reduced state of system S due to interactions with BAF will tend to thermal equilibrium state that's analogous to the initial state of the BAF, right? So we are interested in long time behavior of our dynamics, which, on one hand, we are sitting in the weak coupling regime. We applied Higgs-Born approximation. When on top of that we have the evolution time is long, it's much longer. We think of the asymptotic behavior, so we want to send time to infinity ultimately. So it will for sure be much longer than the correlation time of the BAF, but also which will be much longer than any other time scale in the problem, which automatically actually brings us to the Markov and the secular approximations we used on the previous lecture when we derived our master equation. So we can do it here as well, right? Long time behavior. So we can take our generator here, which I will write like this: L2 U0 du, and when t, just to indicate that t goes to infinity, so that all the timescales are much shorter than t, so that we are justified in applying secular and Markov approx on top of everything, which will lead us to the Davis generator, which in this case I will denote in the following way. So we'll have the Hermitian operator J, the Hermitian part of the Davis generator, plus, due to secular approximation, we have sum over frequencies. We will have here a coefficient W depending on omega. I will define them shortly. And we have the the characteristic GKLS form here. It's a little bit simpler than what we saw on the previous lecture because because our coupling, we don't have sum over alphas here, right? So the structure is much flatter, it's much more simpler, less coefficients, less operators involved, less jump operators involved, right? And we also have to have this anti-commutator bit here, right? So this is Davis generator in Born Markov circular approximations. And what are the pieces it is made of? So first, so we have here a set of all the frequencies involved in our dynamics. So this omega contains all unique frequencies of the form HS A minus HS B, where HS are eigenvalues of the shifted Hamiltonian. HS acting on ket indexed by A gives us SA A and A forms an orthonormal basis in S, right? So we take an eigenvalues of our shifted Hamiltonian. It is a constant due to stationarity of the environment. It is constant operator, so we don't have to worry about time. And we can grab all the frequencies, so the differences, unique differences, unique value of frequencies made out of energy level differences. And this is what defines the range of the sum here. It also defines for us the frequency decomposition of the coupling operator as omega. Rec decomp of the coupling. I'm basically like repeating the definitions of stuff we used previously when we are doing our Born Markov discussion on Born Markov approximations. So S omega is defined as, let's not my notes, yeah, sum over indices AB such that we have delta omega AB A AS B B. So as a shorthand, I will the matrix element of operator S AB SAB. Okay, so this will be a matrix element. So this thing, right? This is a shorthand. So this is the frequency decomposition. So we understand this guy. We understand the sum over frequencies. Now this coefficient here, the transition rate as I will call it, transition rate. So on previous lecture, we had here a whole matrix of coefficients. We found out that it's positive semi-definite, this matrix, as is required by GKLS form. But here we don't have, the coupling is simpler, right? No sum over alphas here. Only one pair of operators is present here, so the matrix changes into just a frequency-dependent coefficient, and I will call it transition rate, and with accordance what we had before, so W index E to remind us that it comes from or is dependent on the properties of the buff. It depends also on frequency and is defined as twice real part of half of the Fourier transform of two-time correlation function E. Let me write it like this. Hopefully it won't be very confusing. So the shifted coupling on the buff side, HEU2, okay, times EIHEU1 F. So I'm writing this in this form just to, to underline that this is a two-time correlation function, and Fourier transform to minus. You know what? Let me, not enough room again. Sorry about that. No, let me rewrite it a bit. I got carried away with the space here. Let me rewrite it a bit differently then. Okay, AIH. Let's write it like maybe T plus U. Okay, this will be better. Sorry for that. T plus U. EIH E U F minus IH E U. The initial condition goes here, and it is a half of Fourier transform. The integral goes over U. Close the bracket. So real part of the half of Fourier transform. Why I wrote it like this? Well, I wanted to underline that this is a two-time correlation function, right? So we have a Heisenberg picture, or should be E here. Heisenberg picture of the observable F belonging to the environment, to the buff, right? Even though it's a two-time correlation function, because we have stationarity, right? So evolution operators commute with the initial state. So I can again do the tricks with where I go to the, move this guy around the. I mean, I can move the evolution operators through the commute with the initial state, use the cyclic property. So overall, I can show using the stationarity that this whole expression here actually depends only on, well, okay. I made a mistake, another mistake. I'm so sorry. dt should be here. Omega t. Okay, so by using the stationarity, right, by juggling the the evolution operators, commuting them with the initial state and using the cyclic property, I can eliminate the dependence of the second time or the first time, however you want to look at it, u, so that the only thing, the only time that this whole expression depends on is this variable t that we are integrating over. Or in other words, the two-time correlation functions for stationary system depend only on the time difference. That's what I should have said in the beginning. That's why the Fourier transform, half of the Fourier transform makes sense here. And that's why I can write it in this way where I have this dummy variable u, right? Because it can be consumed. So poof, that was pretty difficult. Oh, I actually want to keep coupling constant here as well. Lambda squared. Okay. So I absorb the coupling constant into transition rate. Okay. And now the thing that we learned on the previous lecture is that this expression here, especially the correlation function, we can use for the thermal equilibrium state. We can use fluctuation dissipation theorem to simplify it a bit. And we can ultimately write it down as, twice lambda square, the thing that we call spectral density, spec. I will use superscript E just to indicate that it is a spectral density characterizing the environment, the buff of omega, and divided by the very characteristic thermal factor, e to beta omega plus 1. And the spectral density, just as a reminder, spec E omega. Spectral density is actually a full-blown Fourier transform of the real part of the correlation function. TF. So I won't be pretending here I don't know about stationarity. So I will already reduce it to the two-time correlation that depends on the difference of the arguments. E minus I omega t dt. Okay, so it's a Fourier transform, the real part of the correlation function. But the real part of the correlation function, this guy can be also expressed as a, this is another reminder, the real part of this trace equals actually 1/2 of trace of anti-commutator of the observable at time t and observable at time 0, effectively E beta. Just a cute little identity that we can show. What else? Okay, so we have so we understand the frequencies, where they come from. They come from the Hamiltonian, the shifted Hamiltonian, not the bare Hamiltonian of the system. We have the jump operators, which then are just are obtained from the frequency decomposition of the operator, of the coupling operator on the side of the system. And we have to here non-negative, okay? So non-negative, they could be zero. Transition rates, which are thanks to determined by the correlation function of the environment coupling. And thanks to fluctuation dissipation theorem, we can express it as this thermal factor, which this will come in place very soon, and the spectral density of the environment coupling operator. What we are still left with is this Hermitian, supposedly Hermitian operator J here, which again, if we just recall what we did on the previous lecture, I don't really have a good name for this guy. So let me just write it, what the J is, operator J. This is, I think sometimes it is called lamp shift, because it's like it behaves like an additional shift to the additional, if you put L Davis here, right? So you will have this additional term that looks like map generated by the Hamiltonian. So this can be like seen as a additional shift to the already shifted Hamiltonian. So that's why it's called like lamp shift. Shift because it shifts energy levels in some way of looking at this. As what it is given by, so this is a sum over omegas belonging to our set omega, of course. Coupling strength comes in, and like transition rate was a real part of the half of Fourier transform. This guy here is a imaginary part of the half Fourier transform of the two-time correlation, but due to stationarity, I can just write one time argument here, beta e minus I omega t dt. Imagine, so this, we got imaginary parts times S dagger omega S omega. And as we showed it on the previous lecture, this operator J is actually Hermitian because of the properties of its coefficients here. So that would be a definition of our problem. So this is our dynamics we will be dealing with, and we want to show thermalization. So formal thermalization, formal definition. So what we are talking about when we are talking about thermalization, where is my note? Here it is. So we will say that the system S thermalizes under the influence of the buff when for every initial state of the system, so whatever you choose as your initial state, the action of the dynamical map generated by the coupling with with the buff initialized in the equilibrium state, which we have our we deployed our approximations here, so let's just plug it back in. AET HS bullet E minus lambda square L Davis times t, okay, rho 0 s. So it thermalizes when asymptotically, when time goes to infinity, this tends to Ps beta given by sum over A minus beta HSA AA. What am I doing? I'm so sorry. Oh, okay. Sorry, some computer almost explode here. Yeah, what I wanted to write is sum over A minus beta HSA AA. Okay, projections onto against sense of the Hamiltonian. And here sum over A, just the coefficients, which equals minus beta H S shifted Hamiltonian trace S E minus beta H S. Right, so we talk about thermalization when whatever you pick as an initial state for your system, over time, asymptotically, you reach a thermal equilibrium state with the same temperature as the bath. Okay, so same beta, that's pretty important. And the energy operator characterizing our system with respect to, so temperature beta and energy levels defined by the respective operator for our system. In this case, it will be our shifted Hamiltonian HS. So what time we have? Okay, good. Good on timing. So our job now is so we have our dynamics characterized, right? We know all the players, right? So our job will be now to basically look at this and to analyze what happens. Is this asymptotic behavior actually there? Okay, what can stop it? But we also want to see what happens before you reach this asymptote, let's say. So we want to see the dynamics of the whole process, dynamics of thermalization, if you will. And the first thing of note, the first thing to note, once all the pieces are set in place, is actually an assignment 34 from the notes. Let me just write it down for you. It's assuming that the shifted Hamiltonian HS is not degenerate. No, I prefer to say non-degenerate. Okay. One word, non-degenerate, which means that all eigenvalues, all energy levels of operator HS are different. Okay, that's what non-degeneracy means. So in the flip side, degenerate operator means that it has, eigenvalues. There are a couple of eigenvalues that are the same value. Okay, so we don't want that. We want each energy level to be unique, which you can mathematically write as for all A not equal B. So indices of the eigenstates, omega I B, which equals the difference between eigenvalues, is non-zero, right? That's why non-degeneracy is kind of, you can imagine that it will become important because if some eigenvalues were the same, you would get like frequencies, zero frequencies would be overrepresented, let's say, in the places you maybe don't want them to be. So assuming that the shifted Hamiltonian is not degenerate, derive. Let me put on the lights. It's not seeing what I'm writing here. Derive the Pauli master equation. Pauli master equation, which is the rate equation obtained from the Davis master equation, Davis ME master equation, that is master equation generated by the Davis generator. Okay, so you want to get rate equation obtained from the total Davis equation obtained by restricting it, restricting it to the diagonal elements of the density matrix. Okay, so that's a assignment for you to work out all the details. I will just I want to look at the solution for it to I want to go over the solution with you here right now, maybe skipping some of the technical calculations, which I will leave for you to do as a homework. Okay, there are a couple of so this cute little assignment. There are actually a couple of very important properties that will of this Davis master equation that we will use very much in our analysis of the thermalization. So yeah, so let's hop in and let's try to derive this Pauli master equation solution. Okay. So there are a couple of things to note because this is so we are assuming we are working under an assumption all the other assumptions plus this one that our Hamiltonian, the shifted HS, is non-degenerate. So this non-degeneracy aside telling us that the frequencies are non-zero, okay, when you have a frequency the frequencies disappear only when the indices are the same, right? So that's there are no like accidental zero frequencies, let's say, it's called like that. But it also means that there is a one-to-one correspondence between energy levels and the labels of the eigenstates. Okay, so non-degeneracy you can you can write it formally in the following way. So non-degeneracy that for different eigenstates in A, B, the values of eigenvalues are different, right? Non-degeneracy, you can translate it directly into following statement that delta of HSA, HSB equals delta A, delta B, right? So in other words, there is a one-to-one correspondence between energy levels and indexes of the eigenstates. This is a technical way of expressing it that will be useful in actual calculations. So we have our Davis generator minus number minus I. We have J, the Hermitian J operator. Let's write down its form. So the coefficient, the imaginary part of the half. Let me just write it. So this guy here, let's just call this coefficient as J of omega, right? Because this is some function of a frequency. S omega S. We have the transition rates, functions of omega. We have the piece where you have a sandwich with jump operators, sorry, minus half of the anti-commutator with S omega S. And this is our Davis generator. So let's take this guy and see. Okay, so it has a couple of pieces here, right? Let's start by taking this piece, the sandwich, and let's act with this on a projector onto one of the eigenstates of the Hamiltonian. Okay, let's see what happens when we do the calculations. And so we have the projector, we know what it is, and we have our definitions of S omega dagger. So we can just write A is already taken, BC. So we have delta omega BC omega. So we expand this guy, explicit form. Let's give it an explicit form. SBC, the matrix element, and we have here BC. We have the projector, AB, and we have the other guy, sum over BC, D, E, maybe not use E because E is for environment, DF, delta omega DF. We have matrix element, but complex conjugate because we are taking dagger here. And we would write here df, the coherence between states df, but we have to take a dagger of this guy. So this will turn into fd. Okay, just flips the cat with bra. And now this is very straightforward to calculate, right? So because C meets A, so you get a delta here. This gives us CA. And on this side, you get A and F, because after dagger, right, F flips to the left side, and we'll get delta A and F. So maybe let me write it like this. And this will result in delta A F. Consult my notes just to make sure I'm not missing anything. All right. So we have sum over B, sum over D, because sum over C and F, we can consume deltas with that, and we'll get this energy frequency delta omega H S of B minus H S A, because C now becomes A. The second delta, this one, omega H S D minus HSA, because F became A, right? We have BA matrix element, this one, and we have DA complex conjugate, because F become A. And what we are left with here is BD projection. Not projection, the coherence between B and D eigenstates. Right. Mm. And now we can draw some conclusions here. Where is it? Okay, here I am. Yes, this is what I got. Okay. So now, if you look at those two deltas here, right? So you see you have omega, minus HSA, minus HSA. The only difference between those two guys is this one energy level here of B, energy of D. So this guy here can be, we can juggle around the deltas to get it into omega BD times omega, no BD. I knew I made something weird. Omega BA. So this is the first delta comes in. I just rewrite it again, and I can use the fact that I can use condition from the first delta to simplify the second delta. And this is what I wanted to say. And when I do, I will get S B H S D, right? I hope you can see it, right? Because those two deltas are two conditions on HSB, D, and A, right? And if you look at this, move around some equations here, you can rewrite it in this form. SBA, SDA, star, BD. And now we can use non-degeneracy here to convert this guy here into delta of BD, right? So this is where it comes into play, the non-degeneracy. And this is excellent because it means we can consume the delta with sum over d, for example, which gives us sum over b wait, wait. Good. Sorry. I, I had some doubts for the second unnecessarily. So we consume this delta. So nothing happens here, nothing special happens here, but the complex conjugate matrix elements, D will convert into B. So we have S, B, A modulus square, and we have B, B, projection onto B. Therefore, a sum over omega W E omega S A, the sandwich. So this piece of the Davis generator gives us sum over B sum over B W E omega B A S B A modulus square B B. This is what I want to write. Yeah. So I use so in Davis generator, right? The sandwich is not the sandwiching is not on its own. Of course, it's accompanied by the sum over omegas and the transition rate. So we use it here. Use the sum over omega to consume this delta here. That's why it's omega flipped into the difference between eigenvalues, which is non-zero when A is not equal B. And we have a projector onto B. So this is one thing. Similar calculations, with similar calculations, we can also solve what happens when you. So look, in this bit, you have a S dagger S, right? In a commutator. Here is S dagger S in anti-commutator. So to like resolve what this piece of Davis generator does to projectors, we have to start by calculating this kind of product here. So with similar moves as we used here, right? We decompose frequency, the S omegas into their form that has deltas and matrix elements. We use the non-degeneracy to reduce some of the deltas to deltas of eigenstates and so on and so forth. You can see in the notes, all the details in the notes, but what you will get from this whole calculation, you will get the following result: B S omega B A S B A modulus, and so we can use this partial result to actually calculate how all the pieces of Davis, the remaining pieces of Davis generator operate. So this thing would take care of this part of the generator, and we can resolve it with only knowing this stuff because sum over omega e omega 1/2. And this I can write as S omega dagger, S omega acting on AA plus, well, I should write here A S omega dagger as omega. But this guy here, I can just rewrite it as S omega S dagger, S omega A, and dagger of everything. So I can just take this result, plug it in here, and just take a dagger afterwards. When I do that, I get this very nicely looking result. So you have A. So the projector is like spit out unchanged, is just multiplied by a coefficient. SBA square W E omega BA. Okay, and the remaining thing is this Hermitian part. Omega J omega coefficient commutator acting on the projector. And it will yield for us using the same technique as above. It gives us A, right? Sum over B, we get our cool little modulus square, and here we'll get J omega BA minus J omega BA, which is 0. So because there was anti-commutator here, those two things just added up. So the action of this one and this one, because you see this is real. It's not affected by the dagger here, right? So they just add up, and that's why we got this final result. And on this side, instead of anti-commutator, we have commutator. So instead of adding up, they subtract, and it's just 0. So what is in summation? Okay, we did all those detailed calculations here, but in the end we showed that Davis map, when the spectrum of the Hamiltonian is non-degenerate, Davis map is such that it takes projectors, okay, and maps them on projectors, on combination of projectors, okay? So whenever you act on, because you see, we acted on a projector, we got projector, even none changed completely. The sandwich changed it a bit, right? You act with the sandwich, you get here sum over B. It's not the same projector as the input, but still a combination of projectors nonetheless. So it means that the Davis map does not kick you out of the subspace spanned by projectors, right? When you take them up to projector, you get combination of projectors. And with similar calculation, which I won't show you here, you can also demonstrate that L Davis, when you take it to not projectors but coherences, B unequal A, it will also keep you in the subspace. Okay. In other words, the Davis generator has a block diagonal form. It has a block diagonal form. So if I split my So if I take a basis in a space of operators of system S, right? Basis made out of coherences and projectors, AB, okay? And I can split this basis into one spanned by only projectors and only coherences, and B. So let's call this BC plus BP, sorry, projectors. BP, BC. So this is a subspace spanned by all projectors. This is subspace spanned by coherences. Then the Davis map is just block, can be decomposed into block diagonal form. Let me write it like this, or using a matrix notation. P, I, J, G. This would be part spanned by coherences. 0, 0. So this is another way of expressing that Davis map. When it acts on projectors, it gives a combination of projectors, no coherences there. But also if you act with it on the coherences, it will give you combination of coherences and no projectors will be found there in the output. So I also took a liberty to splitting this coherence part into 2 bits, one representing this. So essentially, this is IJ, supposed to be calligraphic font, because this Hermitian part of the generator, as we just found out here, where is it? Oh, it acts trivially in the projector subspace, right? It's just always 0, so you can just ignore it when you look at projectors. But it does something non-trivial when you look at its action in the coherent subspace. So yeah, so this property is very important. Okay, so we just showed that when the shifted Hamiltonian is non-degenerate, you can look at the dynamics of the diagonal part of the density matrix independently of the dynamics of the diagonal elements of the density matrix. Hence, the assignment was to, just to remind you, the assignment was to derive a Pauli master equation, which is a master equation when you take your Davis master equation and restrict it to the diagonal elements. This, what we show here, that this block diagonal structure allows for doing this kind of restriction, because we know that the equation for evolution of projectors will be closed, right? Because the action of the generator cannot kick you outside of the subspace because it's block diagonal. And so let's just to finish this off, let's write down what is the form of this Pauli master equation, because we will use it soon. Oh, one, more thing to note. because Davis generator is not everything. We also have this. So this is block diagonal, and we also have the, let's say, the free evolution of the system as well. But this is pretty easy to show that it's also block diagonal, because if I take a generator and act on coherence of projector element of basis B, these guys are simply eigen operators of HS. Because if I just write down what the action is, HS. So, this is eigenvector of this operator. So you get HSA. Same here, minus HSB. AB, which we actually call omega AB. Right? So it's the free evolution is not only block diagonal in this basis, it's actually diagonal in this basis. So in particular, it's also block diagonal. So still, it won't interfere with our restriction to only the diagonal elements of density matrix, aka the BP part of the space. So having this out of the way, we can now just write down the Pauli master equation. Pauli ME. So we take a time derivative of a diagonal element of the density matrix, of the system density matrix, which we come in with the derivative under the matrix element. Rho of t is just minus it. It's a dynamical map. Minus lambda squared t L Davis. Acting on rho 0. S. Close the bracket. Which simplifies immediately to Davis rho 0. No, sorry. Rho TS A. Well, this is because those two commute, and this acts trivially. This map acts trivially on the diagonal elements, because its eigenvalues are 0 for projectors. And we continue. So we can write it like this: A minus lambda square L Davis acting on B rho TS B projection on B. Right? We already know we can simply disregard all the pieces of the density matrix spanned by coherences, because we are taking the diagonal element, right, of the whole thing, and the action of Davis operator will maps coherences onto coherences, so they will be automatically eliminated by taking the diagonal part. Okay, so we can simply ignore everything except for the diagonal elements, the elements spanned by the projectors. And this guy is therefore equal to sum over B, the elements rho ST B and A M acting on B, B taking A. Right, this is what I just argued for. We are operating in this block, so the M part, the superoperator M, so we need to calculate this stuff. And now, we have our we understand what is the action from those previous calculations. We have derived what is the action of this projector part of the Davis map. In those two pieces of calculations, we figure out what is going on exactly, so we can just use it here to rewrite this stuff in the explicit form. And what we are getting here is so it's sum over B. B rho T S B. So this matrix element and the action of this guy here, it just simplifies sum over C W E omega C B S C B modulus square C projection minus B projection onto B. And and one more bit, we are not to be forgetful about taking the we are looking at the element A of the diagonal. Okay, so those guys are here. So essentially, this part comes from the sandwich. From this, and the other part with a minus comes from the anti-commutator. All right. So this is how it looks. And now we can okay, so now we can do more transformations here. So let me rewrite it like this. B sum over B, open parenthesis, WE omega AB, the matrix element, AB square, B rho TS B minus, so the other bit, omega BA. So I'm basically changing names of the indices under the sum, right? Because I have sum over C here, sum over B. So I can now, basically change the names of C and B at will. So I'm doing that here. Minus SBA A. What I cannot change is the A index, because this is the matrix element I'm taking. But I can write it like this. So this almost looks, this already looks like some matrix acting on a vector here, right? Sum over B. This would be like indices of this matrix, AB. acting on this guy. But this one is weird because this, this is like it wants to be a matrix acting on the component of vector, but there is no sum over A here. But we can fix that a bit with some magic here. Sum over B, WE omega AB SAB minus delta AB sum over C omega B, no, not B, CA, CA SCA squared acting on B rho T S B. Okay, so by putting in here delta, I put in delta and sum over B, and I change the name of this index B to C, essentially, just to make it look like a matrix acting on the vector on the right hand side, so that I can write it as B M A B acting on B rho T S B. So you take a time derivative of the element A of the density matrix at time t, and on the right hand side you get some matrix B acting on the diagonal elements of the density matrix at time t. In other words, this is a master equation, Pauli master equation to be precise, and it governs the time evolution of the diagonal part of the density matrix. And it can be obtained from the Davis generator because for non-degenerate HS, Davis generators is block diagonal. So you can just focus on the diagonal part of the density matrix independently of the diagonal part. All right, and so that was quite a bit of work. Took more time than I expected, actually, but this was important because now this will direct our discussion a little bit better, because we are still trying to describe the dynamics of thermalization. Okay, so having done this assignment, having showed the Pauli master equation and having shown the master equation for the diagonal, this block diagonal structure for our dynamical map, now we can move to next part, 6.2 H theorem. Okay, so we have our block diagonal stuff. We have our Pauli master equation. And now let's note the following thing. So this is a Pauli master equation, right? Okay, that's good. And we take note that the thermal state, so P as beta, defined with respect to our non-degenerate shifted Hamiltonian, not bare Hamiltonian, but the shifted Hamiltonian, trace S E minus beta HS. Okay, that this guy, thermal state, is a steady state solution to Pauli ME. So we can show this. This can be shown. So steady state solution means that when I take when I substitute P as beta for rho Ts, and I plug it into the Pauli master equation here, the right-hand side will be 0, which means that this is the solution that's static, steady state solution, right? The thing that doesn't change in time at all. And we can show this quite easily. We can show this. Using the crucial property of transition rates. The property I mean, it is called detailed balance. Detailed balance. Detailed balance. And there are a couple of ways of expressing it. This is a special symmetry of the transition rates. In one way to express it, it's like you take a transition rate minus omega. So we can imagine, omega frequencies, they come from differences between energy states, energy levels, right? So transition rate of omega, you can think of it as a probability to transition or the rate of transition, that's why transition rate, from the one energy level to the other energy level, such that the difference of energies between them is omega. So when I write transition of minus omega, so I have two energy levels, the difference between is omega. I say minus omega, so I'm saying that I'm transitioning from this upper state to the lower state, let's say, okay? The W of omega, of plus omega, would be transition the other way, okay? Detailed balance is it tells us how those two transitions in opposite ways behave, okay? What are the symmetries of these transitions? And this is, you can easily calculate what's going on here. So we take spectral, we take the explicit form of our transition rate, minus omega. I just write it down as is. And we have the thermal factor, because we're taking minus omega, so here we have E minus beta omega. Now, the thing about spectral density is that it's symmetric in omega. You can see it from the definition. You can see from the definition because it is a Fourier transform of a real function of time. So therefore, from the properties of Fourier transforms, the Fourier transform of real function is symmetric in omega, okay, and in frequency. That's a basic property of Fourier transform. So spectral density is always symmetric. So here you will get lambda omega spec E omega. This is for free, but in the denominator, so I can do this funny trick. I just extract E minus beta omega, so get 1 here, and the 1 when I extract the factor, I get E beta omega with plus, okay, with plus. But this thing here, so spectral density of omega and the factor with plus beta omega, this is just W E of omega. And what is left is this factor here. So when I move it from denominator to numerator, I get E beta omega. Or the other way to write it down is WE minus omega. The ratio is E beta omega. This is this is called D-Tate balance. So this interpretation, what is the meaning of transition, right? That let's say transition of WE omega. So this one would be a transition rate from, let's say, this energy level to this energy level, such that the difference between them is omega. And then W of minus omega would be transitioning the other way, other direction. And you get that the ratio between them is set by a temperature, okay? By the bath temperature. And this very specific, very specific form of E to power beta omega. Omega, again, is the difference between energy levels. So this is pretty big. This property will come up all the time while we'll be analyzing our system, the dynamics of the thermalization. But here in particular, we can take this guy here to show that this thermal state, which again I can write it as let's write it like this: Z as beta. So this trace here is called sometimes statistical sum. And this part I can write explicitly in terms of energy levels. Okay, just to be just to have it the explicit decomposition of the density matrix in terms of projectors, right? And I get values. Okay, so we want to show that this density matrix is a steady state solution of Pauli master equation, which amounts to saying that this operator is this operator is a eigen operator of the Davis generator that corresponds to zero eigenvalue. That's the other way of saying this. So we can show that. So minus lambda L Davis acting on P as beta minus lambda Davis acting on 1 over Z as beta, so statistical sum plus a beta HSA AA, again, to just have it explicitly written down that it's spanned only by projectors, so we can use the property of L Davis being block diagonal, so that we can write it down as statistical sum is just a constant, just a, and we can use our the block on the projector part of the generator denoted by M, which we can push it further, simplify it further as beta AB B M B A E minus beta H S A B. So we just used our matrix representation of the generator M, of this diagonal part of the generator M. Uh, yeah, let me follow some calculation because I want to show how the detailed balance enters this whole story. So again, we have our formulas for MBA, 1z s beta sum over AB. So we get B E minus beta HS HS B and the matrix elements omega AB S AB modulus square minus. So I'm just putting here the explicit formula for this matrix element. HSA WE omega BA BAS BA close brackets and cat here. All right, so this is a modulus square of the matrix element, so it's symmetric. You can because S operator S, not its frequency decomposition, operator S as a whole, because these are matrix elements of the operator S. S is Hermitian, so modulus square doesn't change when you flip indices here. So you can do it freely here. So that's the first thing to note. B, so I can extract AB as factor ABS from everything. But the other thing to note, just omega AB, right, is a difference between energy level HA and HB. Therefore, omega BA is minus that, right? Because this thing here equals HA minus HB, right? So this guy here equals HB minus HA, which equals minus omega IB, right? So this is a transition rate from, let's say, B to A, if you want to view it in this way. So then this guy is a transition rate from the other direction, from A to B, all right? So as you can imagine, this is where detailed balance will come in. Yeah, E omega IB minus E minus beta HSA WE minus omega IB. That's cool. But now we have minus omega IB, so we have our detailed balance. This thing will be equal this 1z beta s sum over AB B WE omega AB matrix element. So here we are left with HSB, and here we have minus E minus beta HS A E beta omega AB, right? But what is omega IB again? This is omega IB is HA minus HB, right? difference of energy levels. That is beta, AB, B, W, E, omega AB, SAB square. And here is where the magic happens. HSA, if you write down explicitly what omega is, A minus beta HSB, so this cancels, right? You are left with E minus beta HB minus E minus eta HB equals 0. Okay, everything cancels because of detailed balance, right? Because we are considering here, because we have transitions between energy levels, and on the level of each individual pair of energy levels, okay, the transition forward and backwards has this ratio set by temperature, and therefore the density matrix that is like made out of energy levels, right? The thermal energy, thermal state, this balance is detailed because it's per level pairs, is such that it all fits. The ratio is exponent of beta omega. The state is E beta omega, essentially energy levels, and therefore everything just works just fine to, so that everything cancels. So if this L Davis is this is the eigenstate with eigen operator, sorry, for the Davis generator with eigenvalue 0. So this means that if I put it here, this matrix, I put it here is an eigenvector of this matrix with eigenvalue 0. So I get so this will zero out if I put here the thermal state, which just confirms the steady state solution. Okay, yeah, this is what we just showed. What else? Well, I can show this explicitly actually. So I take the derivative. So I set my or the other, okay, the other way of putting this, that is a steady state solution, is say I place my initial condition to be this thermal state, okay, beta. So then the rho of T would be E minus IT HS E minus L square T L Davis, right? Acting on P as beta, right? Right. This is what we're doing. Since this is spanned only by projectors, we can just take only the projector part of the generator M acting on as beta. But we know already, we just checked, we just showed that P beta is a eigen operator of super operator M with eigenvalue of 0. So it's very easy to act with it on with this map on P. HS0 ET0, right? Because eigenvalue is 0. In other words, nothing happens. And well, and all we are left with is the action of the free evolution. But you know, since as beta, since P is just a function of HS anyway, this guy is commute, so I can move this. I can move this evolution operator to the left, and it will cancel with the evolution operator on the right. And we cancel with this one, with this evolution operator, and you will be just left with z as beta e minus beta hs, which is just p as beta. In other words, does not evolve under the action of the Davis map. Or in other words, is a steady state solution. So this property, thermal state being a steady state solution for the not only Pauli master equation, but also for the Davis master equations, is already a good, it only makes the thermal state a good candidate for it being a equilibrium state, okay? Because we know that if the system S happens to be in this thermal state, happens to be initialized in this thermal state, it will remain, everything will remain static. So this is like, which means you are at the equilibrium. But this is not enough, right? Because you don't only want, not only want this thermal state to be the steady state solution, you also want it to be an attractor for any other state. That is, you want, what we really want is to see that whatever initial state you set for the system S, the Davis map will take this state and bring it to its steady state solution, to the thermal equilibrium. So the steady state solution is then an attractor for this master equation. Okay. So to get the full picture, right? Or the other, no, to be able to say that this P beta is thermal equilibrium, we also have to show that it is this attractor. Okay, and this is where the H theorem comes to the rescue. This is where the H theorem comes to the rescue. Okay. Okay, so subsection is entitled H theorem. So far, we haven't even mentioned what it is. We just found out that we have this steady state solution and we have detailed balance. So we have those two pieces. Now okay, what is this mysterious H theorem? Well, okay, so another thing to note is that if we focus only on the diagonal elements of the density matrix, so those things the Pauli master equation is for, okay? Hey, those guys, because density matrix is positive semi-indefinite operator, all the values on the diagonal must be non-negative. Okay, that's one. And because the density matrix has unit trace, the sum of all those diagonal elements is one, which means that so you have for every A, this is non-negative, and sum over A rho S T A equals 1. So in other words, the diagonal elements of the density matrix always can be interpreted as a probability distribution. Okay, good old probability distribution. In particular, the diagonal elements of this steady state solution, they are also a probability distribution, right? By the same token. Also a prob dist distribution. So they are just normal probability distributions. We can, if you focus on the diagonal, it's just like looking at the standard probability stuff. And so we can invoke some classic results from the dating back to works of Boltzmann and other classics for the thermalization in classical systems. And one of those classic results is the H theorem. With the name, maybe it's not very revealing, but it comes from the symbol used by the Boltzmann, I think, originally for something called the relative entropy. So you have something called relative entropy. So H of T, so following the convention of Boltzmann, equals I will in a second we'll explain what this diff means. Diff between rho TS, this probability distribution, and P as beta, and this probability distribution. That is defined by the following formula. A rho ATA natural logarithm of rho AT, not A, S, 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 A divided by P S beta A. Okay, so what relative entropy and this function A is what is called this function is something that's called a statistical distance. Okay, so mathematically speaking, this formula here can be understood as a kind of distance between two probability distributions. So rho t and in this case the p beta, so the thermal equilibrium distribution, and it's kind of like a distance. Formally, it's called divergence because it has all the properties of distance except that it's not symmetric, right? Because the standard distance between, let's say, two points or something, it doesn't matter which one is on the left argument, which one is on the right, but the statistical distances, formally called divergences, are not symmetric like that, but they have all other properties that a distance like. So in particular, this ht is 0 only when rho st a equals p as beta a for all a. Okay, so in particular, that this H, the relative entropy, this divergence disappears only when those two probability distributions we are using here are exactly the same. So in other words, H of t is large when there is big difference between rho t and the equilibrium distribution. And the H theorem we want to investigate right now tells us that this H of t can only shrink in time, okay? Meaning that over time, any probability distribution for our system A, the diagonal of its density matrix, will come closer and closer and closer and closer to the thermal equilibrium, and eventually, so it can only shrink. Oh, I forgot to say it's a distance, so it's a non-negative number. So you start from some distribution, initial distribution on the diagonal, and H theorem, which we'll show in a second, tells us that this distance can only shrink. So you will shrink, and at some point it cannot go anywhere else but to zero, meaning that our initial probability distribution over time just was attracted to or converged to the thermal equilibrium. And this is what we want to show, that it's not only that the thermal equilibrium is the steady state, so when the system is initialized in this state, nothing changes anymore, but also that wherever you initialize it, over time it will actually fall into this steady state solution. So so that it is an attractor. So this is what we would call the thermalization. So H theorem states, it basically states that dTHT is negative. So the derivative is negative, which means that the distance, this divergence between probability distributions will only shrink. Okay, will shrink. Oh, it can reach zero when, at some point when actually the probability becomes identical to the thermal equilibrium. Okay, so this is the statement of the H theorem. Like I said, this is a classic result from classical statistical physics, essentially, non-equilibrium thermodynamics. But because of the properties of Davis generator and the density matrix, we can actually take it here and apply it even to quantum case, at least in partially. So let me go over a bit. Let me dive into the H theorem, the proof of H theorem, to again pinpoint what is to actually show you that again, detailed balance, this little property here, is a crucial ingredient of this of this explanation for thermalization. Okay, so let's just do the calculation then. Proof. So we take a time derivative of h of t, right? And what it is. So, here's the formula, here is the dependence of time, on time. So we get d rho tsa. So we can hit the first term with a derivative, leaving the logarithm unchanged. P as beta a. Plus we have the second term where the derivative hits the logarithm. And the derivative of logarithm is 1 over the argument of logarithm. So we can write it here as beta A rho STA, which is fine because this will cancel here. And we will have a, the only row depends on t. So we'll get 1 over P as beta A, derivative of row STA. This also cancels, this cancels. And now this thing here, this is equal to, I can stick the derivative outside the sum, rho STA, but this is norm of the probability, right? And this is constant and equal to 1 always. So this does not contribute to the derivative. And that's cool. So the only thing we have to worry about is the derivative of the diagonal element of the density matrix, but we have Pauli-Master equation for that. So we can just put master equation here. So we can write it like this, sum over AB, M AB, rho STB times logarithm rho STAB, P as beta A. Okay, that's cool. And now I will do something, a mysterious trick, which won't be clear why am I doing this immediately. So what I will do now, I take this sum, I split it in two, to 1/2 here, 1/2 here, and in the other 1/2 I will change the name of indices exchange the name of indices. So I will rename B as A and A as B. So I will have 1/2 AB. Again, and this is these are all classic moves, let's say, from back when first the thermalization was considered in classical physics by the likes of Boltzmann and Gibbs and all those other famous theoreticians. So this is the other half where I exchange the names of variables so that I have MBA rho STA logarithm rho STB. I know I changed everything, so you have to keep track of what's going on. And now, why would I do something like that? Well, this is where detailed balance comes in, because detailed balance gives you a certain symmetry between transition rates. And those transition rates, they define the matrix element of our dynamical map, right? So the symmetries of detailed balance of transition rates will translate into certain very potent symmetries of the matrix M. In particular, let's call it symmetries due to detailed balance. In particular, if I take MBA, so this guy here, right? And I write down explicitly what it is. So it's WE omega BA SBA square minus, this is this other, oh, I need my delta here, delta BA sum over C WE omega CB SCB. Okay, so now I can do some shenanigans. So omega BA is minus omega AB. SBA modulus square is SAB modulus square. We have delta BA, so I can change this B and this B into A without any cost because, I have delta here. And also delta is symmetric. So I can write it like this. WE omega CA square. Okay. That was quite easy. So now I can use detailed balance to convert it into W omega IB with the cost paid in the form of a exponential coefficient omega B omega AB W omega IB SAB. And I can also, because I have here delta, I can also write here beta omega IB without paying any costs. Because delta means that I have, this omega IB here is actually omega IA, and omega IA is the difference between the same energy levels, which is 0. So essentially I'm multiplying this by 1 here. Okay. Omega CA square, but it allows me to extract this exponent in front of everything, P omega AB. And what I will, when I take those guys out, what I'm left with is just MAB. Okay, so I started from MBA, so this guy, and I transform it into MAB plus a correction. And what is this correction? So let me write it like this. HSB divided by minus beta HSA. So let me also write here statistical sums. So statistical sum divided by statistical sum, aka 1, AB. And this gives me P as beta B divided by P as beta A MAB. Okay, so now this form, you can imagine, will come in handy here. So now there is a bunch of, so when I take this relation, I put it here, and I start doing even more unintuitive algebra, but it's all, again, classical moves, as I called it. People figure out like 100 years ago or more. So I will skip those details after I will skip all the details after I put the MBA with this using this symmetry. If you want to see everything, how it goes, all the steps along the way, check out equation 308 in the notes. Okay, the details for details. I will just give you the result. So after all is said and done, the derivative of over T of HT of H, the divergence can be written as 1/2. You have sum over AB. You have W omega AB. That's cool. SAB. That's cool. You have the PS beta of B, the probability, and here comes the very specific combination we are trying to achieve of the ratios. Is beta A minus rho STB times logarithm of those ratios. Rho STB divided S beta B minus logarithm of the other guy, STA PS beta A. Close parenthesis. And now, a couple of things. This is a spectral density divided by E beta omega plus 1. So this is non-negative, okay? This is modulus square. This is non-negative as well. Could be 0, but it's never negative. This is a probability distribution, again, non-negative. So these all guys are greater or equal 0. That's cool. So we have a sum of factors where at least a half of those factors is never negative. And then we have this weird combination. And actually, we can show using concavity of natural logarithm that this thing here, this combination here is non-positive. As a matter of fact, this thing here is 0 only when those ratios are equal. In other words, this thing is negative when the probability distribution rho T of S is not exactly the same as probability distribution P as beta. Okay, if there are at least if they are not completely identical, then this thing will be negative, strictly negative. So where does it come from? So let me write it like this. So what we have here is y minus x logarithm x minus logarithm y, okay, which equals y minus x logarithm x over y, all right? And this thing is less than equal to this, which equals x minus y, x sorry, y minus x, x minus y, divided by y, which is never positive. And why this? This comes from concavity, because you have logarithm of some eta minus logarithm of some eta minus logarithm of some mu. This is because of concavity, it's mu minus eta minus mu times the derivative of logarithm at point mu. That's the definition of concavity, or a consequence of, well, yeah, it's one of the definitions of concavity. Given what the derivative logarithm is, this simplifies to eta minus mu minus mu. And now if I set mu equal 1, eta equal x divided by y, I get that logarithm xy is less equal y minus 1. And I can, so this is where this came from, okay? It's concavity. Concavity of logarithm. Right. So we got here. So in other to summarize, so this h is a distance, statistical distance between the density matrix at time t, the diagonal density matrix, and the target, the steady state solution, the thermal equilibrium P. Okay, and we are showing here that as the time passes on, so the evolution goes on, the evolution due to Davis map. The distance, the divergence between our state and the thermal equilibrium will be shrinking. Okay, will be shrinking. And then it eventually reaches zero, and it reaches zero, as you can see here, only when those ratios are exactly the same. Those ratios are equal 1, essentially. Each ratio is equal 1, which means that the probability that our state is the same as the thermal equilibrium. And at this point, you reach the distance 0, so you reach the thermal equilibrium. And at this point, the further evolution stops because the thermal equilibrium is a steady state solution, right? So this shows that you have this equilibrium solution, the steady state solution, is an attractor of this master equation, right? Which means that at least for the diagonal of the density matrix, the diagonal will tend over time to reach the thermal equilibrium eventually, which is what if we just look on the diagonal, this is what we want from thermalization. And there are a couple of caveats to consider here. Because we wanted, so what we want from this, we want to see that the distance, the statistical distance, will decrease, and it will be decreasing until the two distributions are the same. Okay, so but it could happen that for some reason, if let's say if this coefficient, some of those coefficients here would be allowed to be 0, right? It would deactivate this concavity contribution, this contribution from concavity, which gives us the negativity of this derivative, which gives us this tells us that you have this convergence of those distributions, right? So if we assume that neither this matrix element here is 0, it's just strictly positive, strictly non-zero, and the spectral density is also non-zero for all those frequencies here, then we have this picture, right? That everything is the derivative is negative, there is convergence, and it stops when they meet because when convergence becomes zero, h becomes zero, it means that our probability distribution has been transformed into equilibrium, at which point it's a steady state, nothing happens anymore. All right. But what happens when there are some of the coefficients here are actually allowed to be zero? All right? So what if sum of WE omega AB SAB is actually zero, right? What happens then? Well, if certain transition between AB is knocked out because either the coupling is zero or the spectral density is zero here, right? You don't have this direct connection between, if this is zero, then you don't have, you cannot link energy level A and B. And you don't have this, you are knocking out this condition that, that tells us that the ratios of probabilities must be homogenizing, okay? But even if connection between the specific NAB is knocked out, here you have a sum over all the possible connections. So it's still possible that maybe a direct connection between A and B is knocked out, but maybe there is some connection with some C that's not B, right? And between B and some D that's not A, right? So you cannot go from A to B directly, but you can go to A from some other places as well. And this will be enough to enable this ratio homogenization effect to take place, right? So even if some connections are knocked out, there still will be others active that will anyway force the probability distributions to homogenize. Okay, for our probability distribution, our state to reach the thermal equilibrium anyway. The only way for this to not happen is to actually have some block of energy levels that are disconnected from everything else. Okay, so we have a block where there is no detour. Okay, but in that case, you have block that's disconnected from all the other energy levels. So what you are looking at this point is like essentially a independent subsystem for your system S. So there are energy levels interconnected, and there is another block of energy levels that are interconnected, but there is no communication between. So this turns into two independent problems of two independent systems, each coupled to BAF independently, and each experiences its own H theorem independent of the other. So, in other words, this is a very robust statement. Okay, there is no way around this effect. This is what I'm trying to say. So this demonstrates that at least for the diagonal of your state, we are witnessing here this thermalization effect. We are seeing here that pretty robustly the thermal equilibrium distribution for the diagonal, right, is an attractor for any initial distribution whatsoever. And this whole thing is enabled by the detailed balance property of the transition rates. Okay, this is what makes this whole thing work. Okay, the detailed balance is the thing that enables the H theorem and also selects the thermal equilibrium of the temperature beta, so the same temperature as the temperature of a bath, as a steady state solution as the attractor. Okay, right? We use detailed balance to show that this is a steady state. Remember this. And we also used detailed balance to show the symmetry, which, believe me, and you can see the details in the notes, that this is required to get to this point, which shows you this attractor property. Okay. So in this way, H theorem allows us to H theorem allows us to conclude that when the energy levels of the shifted Hamiltonian are not degenerate, we will have this attraction. We will have this at least first stage of thermalization. But this is not. But this is just like a. Okay, it gives us H theorem on its own. It's pretty powerful because it shows that there is a steady state. That there is one steady state where all the other initial states will be attracted to. That this is a powerful statement, but it does not explain how the dynamics of this process actually happens in time, right? So this is what I would like to move to talk right now. And yes, so let's move to talking about the dynamics of the process. This is 6.3, the eigen system analysis. All right, so we know what happens eventually in our system, but to see how it unfolds in time, we have to do something extra here. And I think the most transparent way to analyze this, the dynamics itself, is to base it on the eigen system of the dynamical map. That is, we want to decompose our dynamical map, this E, at least on the for now. Let's stick to the subspace spanned by the projectors. So we have our L Davis equal M plus IJ plus G. So we understand that M satisfies the H theorem. So we know that it leads us to thermalization eventually. But to see how the dynamics unfold, let us try to investigate what is the structure of the eigenvalues and eigenvectors or eigenoperators in this case of M, to actually to rewrite the action of the dynamical map in like more transparent way. So as a preliminary to this, okay, so if you want to do a proper eigensystem analysis with the easiest case is when your super operator or your operator, depending on in what context you are working here, when it's eigenvectors or eigenoperators in case of M, form a basis, an orthonormal basis in your space, right? Then you can like any solution of the master equation then can be decomposed into into this basis, and you can easily compute how each of those components independently then evolves in time under the action of the of your map, right, generated by this by the generator, by your generator. But to have this decomposition, to have this thing that eigenvectors, eigenoperators form a basis, well, your generator, your superoperator, it has to be a Hermitian or more generally a normal matrix. Okay, so the first step in doing the eigensystem analysis is to actually demonstrate that generator M is normal matrix, that it does have the full set of eigenvectors in which we can decompose every solution into, okay? And the funny thing, the funny trick about this is that M turns out it is Hermitian, but Hermicity is with respect to a given inner product in your space. And M, we can show that M is Hermitian with respect to very specific inner product. Because so far we used in the space of operators, we use this inner product defined with trace. Okay, AB. This was inner product in space of operators. And this is very fine, very good standard inner product. So we could test for Hermicity of M with respect to this inner product, but we wouldn't get it actually. As it turns out, you need to define the special inner product. Let me encode it like that. The special inner product that actually is in tune with the symmetries provided by the detailed balance of the whole problem. This is quite fascinating stuff. And let's define this inner product in the following way. So there is a beta HSA, right? So the energy level and temperature comes in, and AB, matrix element of operator A, and B, and this whole mysteriously looking expression, this can actually be also written as a trace, but not just trace where you have an additional metric inserted into your trace. So this thing here translates into this. So you see, this is not the same kind of inner product, but this is an inner product. This has all the properties of the inner product. You can use it to define norm. Everything is fine. And in particular, you can test. So inner product. So it can also define for you what it means that things are orthogonal and normalized. So you can have orthonormality with respect to this inner product. And things that are orthonormal with respect to this inner product doesn't have to be orthonormal with respect to this standard inner product, and vice versa. Okay. But we can also now we can check for Hermicity of M with respect to this specialized inner product. And we will find, when we do the calculation, when we do the calculations, we actually get it. So let's show that M is Hermitian. MB as beta. So we just okay. M is the block that operates inside the subspace spanned by projectors, right? So this inner product will when you put M acting on B, this will automatically like cut out only this block, this projector span block. So instead of double sum, we will have here only sum over only one index, and essentially diagonal element matrix elements of our operator will be counted here. E beta H S A. So that's why so this is a reason why I have only AA here. But then the action of B, action of superoperator M. So again, we have our matrix elements M, which we can deploy here. BB. So it depends on index A. So this sum is not entirely trivial. And now what I can do, I will shuffle around the thermal coefficients here. So I take this guy and put it here and multiply and divide by e to beta HB. So I'm getting this sum over A. Actually, not sum over B. Sum over B here. E beta HB. So I multiply by E beta HE and they divide by eta BHB. But I will absorb it immediately to the second part of the sum. Beta HSA. So this guy is the same as this guy, divided by E beta HSB. So this is, multiply, divide, this is the denominator. And I have M A B A A. Let me take complex conjugate. Matrix elements of M are real, so complex conjugate does nothing. So I just extended this complex conjugate from A to this whole sum here. And we are left with one more factor, B, BB. Okay? And now we have sum over B, E beta HSB. And we have here sum over A. The ratio of thermal factors, well, this is very close to the ratio of probability distributions. We just flip the sign a bit. MAB, AA, complex conjugate, BB. But this thing here, okay, we can use our detailed balance induced symmetry to basically go other way, go from here to here. which will give us sum over B, E beta HSB, sum over A, M B A star B B B, which is nothing else but M acting on A, B as beta, which means that it's Hermitian. This is how you define Hermicity. But you can take M acting on B and move it to be acting on A. No, it's when you take M acting on B under your inner product and you move it to be acting on A instead, and M doesn't change, that's what Hermicity is. Self-adjointness. And so it is Hermitian. Therefore, it has its eigenvalues are real, are purely real, okay? And its eigenvectors, eigenoperators, form an orthonormal basis, orthonormal with respect to this scalar product, okay? Not necessarily this one, but this, because this is where Hermicity is, okay? So in other words, eigensystem for M. So we have M acting on operator Q of mu, gives you mu times Q mu. So this is eigenop, eigenval, and they are real. Okay, they are real. And these guys, eigenoperators, because of Hermicity of M, they form a basis, which means that you can take identity in the subspace of projectors, because M is a block that operates in the projectors. It has 0 everywhere else. So the composition of identity in terms of its eigenvectors works for this subspace only. And we can write it as and you can write it as like this. So we have eigenvector here. You have as beta, and so we haven't bothered to normalize Q's yet, so we have to take care of the normalization here, divided by null. So what this formula is, so if we were talking about cat spaces, the things you are familiar with, so you would write that 1 equals sum over, let's say, some eigenvector A, and you would write something like this: A divided by A. Right? This is what you would write. So what is bra actually? Well, bra is you take an scalar product. Bra means it is a the one part of the scalar product between two vectors, right? So you would write it something like this, so that A acting on some B, right? You would just put A, B. Okay, this is what bra means. So this is the bra, but for this our specialized inner product. So this is how we can define it. So let me erase this thing. And we know, so we have our real eigenvalues, and we know already that there is at least one eigenvalue 0, the one corresponding to the steady state, right? Because we already know. We know from before that M acting on P as beta is 0, right? So we know, which means that Q0 equals P as beta, okay? We also know that this is the only 0 eigenvalue for our superoperator M, because if there was some other 0 eigenvalue, that means that there will be other steady state solutions, okay? But that would contradict the H theorem, because H theorem tells us that whatever you pick as your probability distribution, it will eventually be attracted by the probability, by the thermal distribution, right? But if you had some other steady state that it's not exactly the same as thermal equilibrium, then there would not be this attraction, right? Because everything will be static, nothing would change in time. But H theorem tells you that over time it's just getting closer to thermal equilibrium, which means that the only steady state, the only 0 eigenvalue has to be the one corresponding to the thermal equilibrium. So we know that there is only one 0 eigenvalue, and it is exactly P as beta. And if we consider a projection in this sense onto this 0 eigenvalue eigenoperator, there's an interesting result. Projection onto mu0 eigenvector, eigenoperator. So the projection would be like this. So we would take P as beta, right? P as beta, bullet as beta divided by the norm, right? So we can just write down what it means. So we'll have P as beta. Let's use our statistical sums here. -1. So here you would have sum over A, E beta, H, S, A, E, beta, H, S, A, bullet A. Okay, if I just put in all the, just apply this definition here and use the fact that P as beta is diagonal. This is what you get. And denominator, so we have two P's, so there'll be -2 power -2, the statistical sum, PA minus beta HSA, E minus 2 beta HSA. Okay, so this is the norm of this guy. So you see this thing just cancels, this thing just cancels with this, and we are left with a sum over E minus beta HS, but this then just equals Z as beta, statistical sum. So it will cancel with one of the powers here, and then it will cancel with this, everything cancels. And we are left with P as beta. sum over A bullet A. But this is nothing else than just trace. All right? And that's pretty cute. And it also tells us, all the eigen operators are orthogonal to each other with respect to this inner product that we defined here. But from this result, we can conclude that for each of Q to be Q mu to be orthogonal to PS beta, they have to be traceless operators, right? Because you want to have orthogonality. So PS beta with Q mu, right? As beta. This is what orthogonality means. But now we just apply our formulas the same way as we did here. And you just get 1 over z as beta trace Q mu, right? This is positive non-zero constant, so this means that the trace of or other Q's for non-zero eigenvalues have to be zero. Just a cool thing to know. And especially it points out to the fact that the zero eigenvalue can be a proper density matrix because it has trace 1, right? All the other eigenoperators have zero trace, so they, in particular, cannot be interpreted as states. So the decomposition into bases of operators Q, of eigenoperators of generator M, is not like a decomposition into different, is some combination of states, right? Because only one of the Q's is an actual state. The rest is just some operators, non-state operators. All right. So we know that there is zero eigenvalue. It is the only one because of H theorem. So the other remaining non-zero eigenvalues are real because M is Hermitian. But what else can we tell about them? Where we can show that all of them, we can show that if all non-zero mu's are strictly negative. How to show this? Well, we can just to show this we have to demonstrate that superoperator M is a negative semi-definite operator. That is, we have to show that when you take scalar product M A on any operator A, whatever you choose as B, this has to be lesser or equal to 0. Then we will know that all the eigenvalues are less or equal 0. And we know that there is only one 0. So all the remaining, then they have only one option to be strictly negative. And to show this, I won't go into a detailed calculation because there is nothing super illuminating about this, I believe. Just some straight up algebra. So see equation 317 for details. For all the details. Okay, but you can show that M is actually strictly negative negative semi-definite, and there is right, it's negative. Okay, so the eigenvalues can be only non-positive, and we know there is only one zero eigenvalue, so the rest has to be strictly negative. And this is all the pieces we need to actually do the decomposition for our dynamics. So if you take the dynamics generated by M, so this is how Davis map acts in the block spanned by in the subspace spanned by the projectors. We can use our because we have found our eigenvalues and eigenvectors, and we know they form a basis because M is Hermitian. You can do the spectral decomposition for M. So we can write this as T sum mu times Q mu. We have bra, right? Our superoperator bra as beta and the norm. Q mu as beta, right? And this then equals to mu E mu T Q mu, the projection, the norm as beta. And then if we extract the equilibrium state, so we can write it as P as beta. So this is the projection on the equilibrium state, right? Eigenvalue is 0, so there is no time dependence here. So mu is 0 for this case. And plus over all the mu's that are strictly negative, that aka all the other mu's, E minus T, right? To show that it's the time dependence is a exponential decay. And you have projections on those other guys, which cannot be, each of those Q's cannot be interpreted as a state because they are traceless, as we discussed previously. All right. And thus, once we have this decomposition, if you want to see how the dynamics works for our system, just take this map, apply it to some arbitrary initial density matrix, use the decomposition, and you will get, as B trace of rho as 0, which is 1, right? Because we start from the density matrix. So this is just the thermal state on its own, not changing in time, steady state solution. And you have the projections on all the negative eigenvalues, which, you will get some operators, Q mu rho as 0 as beta divided by norm, all in with respect to this specialized inner product, and easily seen that the time evolution is extremely simple then, because the steady state remains there as it always was. Let's say the projection onto steady state remains there, it unchanged, and all the other parts of the density matrix, initial density matrix, all decay exponentially. One goes faster, one goes slower, all depending on the value, on the actual value of the non-zero eigenvalues of M. Therefore, you go send time to infinity, the only thing that will remain is the steady state solution. Thus explaining H theorem and all the other stuff we were talking about. So this is this I think is a kind of cute explanation for the overall dynamics of the process of thermalization, how it occurs in real time, let's say. But this is not all of it. Okay, this is not all of it, because there is this is only what happens on the diagonal of the density matrix. But there is still the whole, the richness, let's say, of the stuff that's going on off the diagonal. And in particular, what we want to see is that the stuff on the off diagonal will always unequivocal. I mean, for the thermalization to be complete, the stuff on the off diagonal have to decay to zero no matter what, right? Because the equilibrium state is only on the diagonal, right? Which brings us to the next step, the phasing. So let me just do a primer here, and I think it will be a proper way to stop for today. So what do I mean by the phasing? All right, so now we take our map, Davis map, T and Davis, and we want to act with it on the other block, the block spanned by coherences. So we want A rho 0s B B, right? A not equal B, so this is the stuff that of diagonal elements of the density matrix. Which means that operator M, superoperator M, which we just analyzed, does not participate here anymore. What does participate is the other bits, what I called I, J, and G. Okay, those guys act on the coherences, right? And they map them to coherences, but what we want from them, we want them as time goes on to reduce everything to zero, right? So that the equilibrium state you eventually reach asymptotically lives only on diagonal, the part where the H theorem takes over and the eigensystem analysis from before explains what's going on. But here are some issues. For one, those off diagonal elements, rho TS of diagonal elements of the density matrix, which I can write as minus EA omega B T trace BA ET I J plus G rho 0s. Those are general complex numbers, okay, not normalized. So we cannot interpret them as a probability distribution. If we cannot interpret them as probability distribution, then this means that we don't have H theorem. We don't have easy access to H theorem to get some powerful conclusion like we got from for the diagonal, right? That there is this attractor that what is the steady state, and so on and so forth. So in order to actually attack this properly, we have to jump straight into eigensystem analysis. However, there is a wrinkle here. So without going into details, you can show that A G B as beta. That so the coherence block part of the generator, I split it into two parts. This Hermitian part IJ and this G here, okay? And the other part, the dissipative part. And you can show quite easily using detailed balance, again, detailed balance property, that G is Hermitian. Let's use this. That G is Hermitian. And also J is Hermitian, or more precisely, IJ is anti-Hermitian, which amounts to the same thing. It means IJ is anti-Hermitian just means that J is Hermitian. Minus IJ A B. So each of them have full set of orthogonal eigenoperators and eigenvalues, which is nice. So we could just do the eigensystem analysis for them. However, the issue is that they don't commute. So we cannot use the same eigenvectors, eigenoperators for J and G simultaneously. And so we need to take care. We need to do the eigensystem analysis for the sum of those guys. Okay, even though each of them is Hermitian, right? So it would be lovely if we could just use eigen operators of one of them, but this one eigen basis wouldn't do to analyze both pieces. So we have to do we have to find eigenstates, eigenoperators for the sum of them. However, as you can see, G is Hermitian, IJ is anti-Hermitian, and so the sum of them, IJ plus G, is neither. It's neither Hermitian nor anti-Hermitian. It's just something else. It's a non-normal matrix. And this means that it's quite possible that its eigenvalues are complex. So it has really an imaginary part. And to make matters worse, it's also possible that there is not enough eigen operators of this sum to actually form a basis, which means that the IJ plus G can be a defective matrix. And so the eigensystem analysis for this off-diagonal part won't be as simple as one for the diagonal part. But to show you some details about it, I think I will leave it for the next lecture. So this will be all for this session, and see you next week.